So as we saw in our last video, there was really no difference in the first two steps in solving for sideways truss, and it's going to be no different continuing on either. Let's go ahead and go to step 3, which would be drawing a rough draft of our free body diagram. So we can start by drawing, okay, we'll draw joint A down here, and we'll draw joint B up above it, and joint C over here to the right. And then we can go ahead and start adding our forces. Okay, we know we got 50 pounds going downward. And we saw for racks earlier, we got 50 pounds as well, okay? So racks going to the right at joint A, which we kind of proved just using kind of common sense and just kind of thinking about it for a second. We found that racks, not even to write out racks, was 50 pounds going to the right. And then we found out that Rubik's was 50 pounds going to the left. We found that out right about here in our notes. So we'd say 50 pounds going to the left. And then we found out that Ruby, which was reactionary force at joint B in the Y direction, was going up, and that was also 50 pounds. And so next what we need to do is go ahead and just start adding our free body diagram, our directional arrows. If we have 50 pounds here going to the left, we've got a force going to the left at joint A. There's no other force at joint A. Clearly, I'm sorry, to the right. This is going to the right. We need a force. Let me pick the right color here. We need a force going to the left. We'll call that vector AC from member AC. If it's going to the left here, if it's going outward towards A, it will also be going outward towards C. If it's going outward, if it's a force pushing outward, we can assume that the member is under compression to push an outward force towards our joints. And now you might be asking yourself, what about member AB? What kind of vector could that be applying? There's no upward or downward force at joint A, so what could that be? Well, we can go ahead and assume that it's tension. You can assume it's compression, actually, if you want to, either one. And if we're wrong, we'll find out with our math later. So I'm going to go ahead and just call this vector AB, and I'll label it as tension, and I'll add a question mark, because we're not actually sure. Keep an eye out for that one, because we might have that backwards. But we will find it out very quickly. Our numbers won't add up, and we'll see, well, clearly this is the problem. So we can just leave that alone for now. But then if you look over here at joint C, well, we have a downward force and a rightward force. Therefore, we need an upward and leftward force, and luckily we have that capability through member BC applying vector BC. And if it's pulling inward from C, it has to be pulled inward from B, and we can call that most likely, it is tension. And so this is sort of our rough draft, what we think our free body diagram should look like. But now we can go ahead and just start drawing each individual joint, which is step 4. Okay, so I'll start at joint A, because it doesn't really matter where I start. I just kind of, it has the least amount of arrows, and I know the most about it, I think. So I'll start with joint A, okay. Well, draw joint A over here on the side, and we'll go ahead and re-add the arrows, just the vectors for joint A. So we got 50 pounds going to the right, and we've got AC going to the left at joint A, vector AC. And what else? Well, we got some random vector here going up, which would be AB, okay. And to start solving for AC and AB, well, first I'm going to say, well, what's the sum of all forces in the X direction at joint A? Well, we know it's 50 pounds going to the left, 50 pounds. Or not just left, I keep saying that. To the right, you can see the arrows clearly going to the right. And we can add that to, well, just AC. And AC must be going to the left to cancel that out. Therefore, AC has to equal 50 pounds. Vector AC equals 50 pounds to the left. And what about the sum of all forces in the Y direction? So we can say, well, what's the sum of all forces in the Y direction? Well, that has to equal 0. And how many forces are there in the Y direction? Well, there's only one, and it's AB. Therefore, vector AB has to be 0. And so since we said earlier that this is tension, it's 0 pounds of tension. For that matter, it's 0 pounds of compression. There's just clearly nothing going on at joint AB, according to our math. And if we're wrong, we'll find that out as we solve for our other forces in our free body diagram. So let's go ahead and go to a free body diagram for joint C. Okay, so we'll draw C, and we can add our forces. Okay, well, we got a rightward force of vector AC going to it, and we just solved for AC. We said it was 50 pounds. It's not going to stop being 50 pounds of compression pushing on joint C just because we went to the other joint. It's still the same member with the same force. Then we got 50 pounds of pressure going down. And lastly, we've got a upward and leftward force canceling out both of those ideally, otherwise this thing would be breaking and someone would be getting hurt probably, of vector BC. Now we can redraw vector BC as we did before. As you can see, like none of the steps have really changed. So we draw our vector BC and we'll go ahead and give it its x and y components. So we'll say, okay, b of x right here. And we will give it a b of y as well. And then I'm just going to, as we usually do, redraw our free body diagram for our joint C. And I'm still going to have, well, we still got 50 pounds here going to the right, 50 pounds. And we've got 50 pounds going downward. But instead of drawing BC, and I'm just saying that I probably should have, rewrite this, made this BC in the y direction, not B in the y direction, and BC in the x direction, not just B of x. Okay, so let me redraw this. We'll say, pencil tool out, we'll say BC in the x direction, and we will say BC in the, well, this is the x direction. That one was the y direction, so I'm just kind of messing up all over here. But BC in the x direction, okay. So now we can finish our free body diagram. We'll say BC in the x direction, canceling out that 50 pounds, okay, and we can see that, well, we got our BCY, my y component of BC, make sure I get the right color here to keep it consistent. Our BC in the y direction, our y component of vector BC, is going up to cancel out our downward force, our original force of 50 pounds. So this is incredibly obvious. We don't have to do much work. We can just say, well, the sum of all forces in the x direction equals 0. And then we can say, well, therefore, we could say BCX is clearly 50 pounds going to the left. And then we can do the exact same thing. We can say the sum of all forces in the y direction equals 0. And since there's only two, we can assume that the one equals the other. Therefore, BCY is also equal to 50 pounds, and this one is going up to cancel out that downward force. So I can rewrite this to say, well, this is 50 pounds, and BCX is also equal to 50 pounds. And I'm going to go ahead and redraw BCY. I'm going to go use my tip-to-tip method and redraw it over here. So this is 50 pounds, and we already solved earlier that this was a 45-degree angle. So again, as you can see, the rules don't really change for solving truss, as I said several times. Just because it's sideways doesn't mean we change our rules. There's nothing really different. But as you can see, there are several different ways to solve for our vector BC. You could do Pythagorean theorem, but I'm going to go ahead and do sine. You could do cosine as well, but I'm gonna just do sine real quick. We'll say the sine of our angle, which is 45 degrees, right in 45 here, in the right color, is equal to the sine, or the opposite, which is what, 50 pounds, or BCY, so I'll write that in right here. 50 pounds is the opposite to our angle, and then we'll divide that by BC. And you can just use simple algebra, or you could divide this by 1 and make it a proportion problem. Either way, you just solve for BC. We can say, therefore, BC equals, and how would we solve? Well, I'm going to divide 50 pounds by the sine of 45 in my handy-dandy calculator. So 50 pounds divided by the sine of 45. And hopefully you see how I know I need to divide it that way. If you're confused, you can work it out yourself. We get 50 root 2. Okay, well, we just hit the conversion button in our calculator. It'll convert it for us. We get 70.7, or I'm going to round to the whole number of 71 pounds. And that is our final vector, or our final member vector. And so all we have left is to redraw our free body diagram with their numbers, which we will do in our